In the last example, we saw a case where there are moments on a cross-section, but we didn't really say anything about how the moments are related to stresses. So let's consider this case. So suppose I have a bar with a moment on a cross-section, and let's have a look in more detail how that is related to stresses and how we should think about it. And this is going to lead to the notion of pointwise stresses now. So one thing to note is that if I have a moment, well, that's statically equivalent, say, to a set of two forces, so a couple. And if I place those at the quarter points from the top and the bottom of the bar, that would be m2 over h, m2 over h. So that's one way to think about it. And so now you see that on the cross-sectional area that the forces are varying from point to point. So talking about average stresses across the cross-section makes little sense in this situation here because the forces can vary. So in general, if I have a section cut and it's supporting a force in a moment, there's going to be some distribution of forces across that cross-section. So one thing I can think of doing is ruling off the cross-section into little bits of area. We'll call those delta A, let's say. And across each little bit of delta A, there's going to be a force. And the sum of those forces, each individual delta F's, is going to generate a force, and the moment associated with each one of those is also going to generate a resultant moment. And in this case, we'll say R is the position vector, say, from some given origin. So that's a resultant moment and a resultant force. But per patch on this cross section, I can define a normal stress, which is the normal part of the delta F that's being supported there divided by the area, so we'll call that delta A, and the shear stress on that little patch we'll call the tangential component of the delta F divided by the cross-sectional area of each little patch. So we get per patch a shear stress and a normal stress. So now we have something that varies over the cross-section of our section cut. And if I consider the limit as delta A goes to 0, so I have an infinite number of patches, I end up with a pointwise definition of stress. So at each point, I'm going to have a normal stress and I'll have a shear stress. And those are simply the density of normal forces being transmitted across the cross-section at that point in the normal direction and in the shear direction. Now, there are a couple important remarks here. First of all, through any given point, there are going to be an infinite number of section cuts that I can pass through that point, which is going to lead to also an infinite number of tangent vectors to each cut. So I'm going to have an infinite number of possible normal stresses at a point, and I'll have a doubly infinite number of shear stresses through the point because I get to pick the section cut, which means a normal vector, and I get to pick the tangential direction. Okay, which now it sounds a little bit complicated, but this is actually really no different than the case of thinking about a vector. We're really just trying to, if you think about specifying the components of the vector, you have an infinite number of choices for the basis against which you're going to represent the components. But what we do with vectors is we just pick a basis, and then we represent the components relative to that. And knowing the components relative to one basis, we can always compute them relative to a second basis. And that's exactly what we do for stresses also. So stress is something known as a tensor, and if I have a body and suppose I consider a point A, what I do is I pass 3 preferred planes through the point A, and I set up 3 preferred coordinate systems, and that allows me to compute the normal and the shear stresses at point A. So if I first pass a point through point a section cut whose normal is EX, then I can calculate a normal stress at A with respect to EX. I can also calculate a shear stress at this point with respect to EY and a shear stress with respect to EZ. So I get a normal stress in the X direction, a shear stress on the X plane in the Y direction, and a shear stress on the X plane in the Z direction. So that gives me 3 values there. So you can see, because I'm going to have more planes to pass through A, this is going to be a much more complicated mathematical object than a vector, but we can do it. So I've passed the X plane through point A. I can pass a section cut whose normal is in the y direction. And so now I'll get a normal stress in the y direction at point A, and I'll have shear stresses on the y plane in the x and the z direction. And I can do it yet again with respect to a plane whose normal is in the z direction, and I can get a normal stress in the z direction at point A, along with shear stresses on the z plane in the x and in the y direction. Okay, so in total, I'm actually going to find, at every point in a body, I'm actually going to find 9 different stresses, 3 normal stresses and 6 shear stresses. Later on, we'll see that we can reduce it a little bit using some other principles of mechanics, but for now we have 9 separate values. To organize those values, we have a bit of nomenclature. So we'll use the symbol sigma for the stresses, and we're going to attach to it 2 subscripts. One subscript is the first one, and that's going to define the face normal that we're looking at. And then the second subscript is going to define the force direction, whether it's normal or tangential to the face that we're looking at. So if I look at a point A, for instance, again, and I pass a cutting plane through it, or section cut, whose normal is in the x direction, then I'll have a little bit of force in the x, the y, and the z directions. And now if I divide those values by the area of this section cut, which I'll call delta AX, then I'll have the normal stress in the x direction, that'll be sigma XX. I'll have the shear stress on the x plane due to the forces in the y direction, we'll call that sigma XY. And sigma XZ will be the shear stresses in the z direction on the x plane passing through our point A. And just as a bit of further notation, sometimes we use the symbol tau when we're talking about shear stresses in this context. So you'll also see tau xy and tau xz. That's entirely equivalent to saying sigma xc. So just be aware of that. You sometimes read that in books. Now there are 9 values, and the way we usually organize them is into a matrix. And so the first index gives us the rows, the second index gives us the columns. So everything in the first column has a second index of x, and everything in the first row has a first index of x. And taken all together, we call this the stress tensor. And the entries of this matrix here, they're the components of the stress tensor in the particular basis that we've chosen. If you choose a different basis, so different set of x, y, and z axes, then the numbers change inside this little matrix here. But the stress tensor is still the same. It's the stress at the point in the body. There's also a graphical representation for stresses, and so it's similar to what we have for vectors. So suppose I have a vector 3, 4. Well, I can go ahead and give it a pictorial version where I have this directed vector, so which goes 3 units in the x direction and 4 units in the y direction. And we just draw in this arrow here as our vector. And there's a similar convention for stresses. The generic just to say a little bit more about this, the generic version for a vector would be you have a component Vx and Vy, and so you have a directed arrow that goes Vx units in the x direction and Vy units in the y direction. Now if I have a tensor here, suppose I have this one here, I'll just do this in 2D, so we'll have no z stresses. So normal stress of 5 in the x direction, normal stress of 3 in the y direction, and a shear stress of 1 in the xy and the yx. And so the way the pictorial convention for displaying this state of stress would be to draw a little square, and then what we do is on the x face we put the normal stress, and we also put its shear stress, and then on the y face we put the normal stress and we put the shear stress. And then we sometimes draw these vectors on the minus y face and on the minus x face. They have the same values as we have on the positive faces. If you have the generic case, 2D again, it looks like this. So you have the tensor with sigma xx, sigma xy, sigma yx, and sigma yy, and then on the square here we put sigma xx, sigma xy, sigma yx, and sigma yy. And so this is the drawing convention if you want to have sort of a pictorial version of the state of stress for a tensor.